Imagine holding an object in midair. No strings, no magnets, no tricks, just sound. Pure, invisible, silent Fourier's sound, pushing against the laws of gravity as if they simply do not apply. This is not science fiction. This is happening right now in laboratories around the world. And the implications are so profound that they could change medicine, manufacturing, and even space exploration forever. Stay with us, because by the end of this video, the way you think about sound will never be the same. We all know what sound is, or at least we think we do. It is vibration. It is waves moving through air, bouncing off walls, traveling into your ears, and triggering the experience of hearing. Simple enough, right? But here is what most people never stop to consider. Sound is not just information. Sound is force. Physical, measurable, real force. When a sound wave travels through the air, it compresses and expands the molecules around it in rhythmic pulses, and those pulses carry energy. Usually, that energy is so small, so diffuse, that we do not feel it. You do not walk through a noisy crowd and get pushed around by the music. But what happens when you take that energy, focus it, amplify it, and aim it with mathematical precision? What happens when you point sound not at someone's ears, but at an object resting on a surface? You get levitation. Acoustic levitation, the use of sound waves to suspend physical objects in midair, is one of those scientific phenomena that sounds impossible until you understand exactly how it works. And once you do, it becomes one of the most elegant demonstrations of physics you will ever encounter. To understand acoustic levitation, we need to talk about something called a standing wave. When two sound waves of the same frequency travel in opposite directions and meet each other, they do not simply cancel out. Instead, they interact to create a new kind of wave pattern, one that does not appear to move at all. It just stands there, oscillating in place. Scientists call this a standing wave. Now, within that standing wave, there are regions of intense pressure and regions of almost no pressure. The high-pressure regions are called antinodes. The low-pressure regions are called nodes. And here is where things get remarkable. When you place a small light object, a water droplet, a polystyrene bead, a tiny biological sample into a standing wave field, the pressure differences in that field create a net force on the object. The object gets pushed away from the antinodes and toward the nodes, the low-pressure zones. And if the geometry is right, if the frequencies are tuned correctly, the object becomes trapped in that node, suspended, floating, defying gravity through nothing but the invisible architecture of sound. The transducers, the tiny speakers that generate these waves, are typically operating at ultrasonic frequencies. That means they are vibrating at frequencies above 20,000 Hz, beyond the range of human hearing. So when you watch a demonstration of acoustic levitation, you see objects floating in silence, or what appears to be silence. The sound is absolutely there. You simply cannot hear it. Now, here is where this stops being a physics lesson and starts being something that genuinely takes your breath away. In a laboratory at the University of Tokyo, researchers have built an acoustic levitation device that does not just hold objects still, it moves them. They call it acoustic manipulation, and using precisely controlled ultrasonic arrays, they can grab a levitating object and slide it through the air in 3 dimensions: left, right, up, down, rotating it, spinning it, all without any physical contact whatsoever. Think about what that means for a moment. You have an object floating in space, and you are steering it with sound, like a tractor beam, like something out of a science fiction film. Except it is real, it is reproducible, and scientists are already building it into tools. But that is just the beginning. In pharmaceutical research, acoustic levitation is being used to study how drugs behave in their purest form, completely untouched by any container, any surface, any contamination. When a liquid sits in a vial, it interacts with the glass, weights the surface. Its chemical properties can be subtly altered. But when you levitate a droplet of a drug compound in midair and expose it to light, heat, or other compounds, You are seeing exactly how that molecule behaves in isolation. The data is cleaner. The science is better. NASA has been exploring acoustic levitation as a way to handle materials in the microgravity of space. In orbit, you already have weightlessness, so levitation becomes less about defeating gravity and more about precise contactless positioning. In environments where contamination is catastrophic, where a single fingerprint could ruin an experiment, or where a droplet of molten material could destroy equipment. Being able to move objects without touching them is not just convenient, it is essential. And then there is perhaps the most astonishing application of all: acoustic levitation for biological research. Living cells are extraordinarily delicate. When researchers study cells, they typically have to place them on slides, dye them with chemicals, expose them to surfaces that can alter their behavior. But what if you could study a living cell? A single, intact, undisturbed biological unit, floating freely in space, observed in its natural state. Researchers are developing ultrasonic levitation platforms that do exactly that. They trap living cells in acoustic nodes, keep them alive, and observe them under microscopes without ever touching them. The cell does not know it is being studied. It just floats there, doing what cells do, giving scientists a window into biology that was previously completely inaccessible. Acoustic levitation did not appear overnight. The science behind it stretches back over a century, rooted in the work of physicists who were trying to understand the fundamental properties of sound. In the 1860s, a German physicist named August Kundt developed what became known as the Kundt tube, a glass cylinder collecting at the nodes of the standing wave. Kundt was not trying to levitate anything. He was just trying to measure the speed of sound. But without realizing it, he had demonstrated the first principle of acoustic manipulation: particles moving to nodes, objects finding their place within a sound field. Decades later, in the 1930s, physicist Louis King published mathematical work describing the forces that sound waves exert on small spheres. His equations were the theoretical foundation that would eventually allow engineers to build the levitation devices we have today. The force he described, now sometimes called acoustic radiation pressure, is real, calculable, and engineerable. And yet, for most of the 20th century, acoustic levitation remained a curiosity, a parlor trick of physics. Something you demonstrated to impress students, not something you put to work in a laboratory. That changed with ultrasonic transducers. As electronics advanced and scientists gained the ability to generate precise, powerful, targeted ultrasonic fields, acoustic levitation transformed from a demonstration into a technology. The last 20 years have seen an explosion of research, with new applications emerging faster than most people outside specialized physics departments have any idea about. Of course, acoustic levitation has its limits. Right now, the objects that can be levitated are small, typically no larger than a few millimeters. The energy required to levitate something scales with its size and mass. And the acoustic fields required to lift larger objects become increasingly difficult to control. You are not going to levitate a car with a speaker array anytime soon. But the trajectory of the technology is remarkable. Each year, researchers are refining the precision of acoustic manipulation, increasing the range of materials that can be levitated, and discovering new ways to combine acoustic fields with other technologies. There are experiments combining acoustic levitation with optical trapping, using both sound and light to manipulate objects at scales approaching the microscopic. There are proposals to use acoustic levitation in semiconductor manufacturing, where contactless handling of delicate components could reduce defects and increase yields. There is even research exploring whether acoustic levitation could be scaled up enough to be useful in construction. Imagine assembling structures in hazardous environments, or moving fragile components in places where human hands simply cannot safely reach, all guided by carefully engineered sound fields. And beyond the practical applications, acoustic levitation represents something philosophically important. It is a reminder that the physical forces shaping our world are far more numerous and far more powerful than our everyday experience suggests. We move through an ocean of air that is constantly in motion, constantly carrying energy, constantly exerting forces on everything around us. We just cannot feel most of it. Sound is not background. Sound is not decoration. Sound is force. Sound is a tool. And as scientists learn to wield it with greater and greater precision, the line between physics and what used to be called magic is getting thinner by the year. So what do we take away from all of this? We take away a lesson about assumptions. So we assumed we knew what sound was. Vibrations, waves, something you hear. And that assumption was not wrong, but it was incomplete. Sound is also force. Sound is architecture. Sound is in the right hands, a way of reaching into space and moving matter without contact. Without contamination, without limitation. We take away a lesson about the history of science. The path from Kunst's powder patterns in a glass tube in the 1860s to a levitating drug droplet in a pharmaceutical laboratory in the 2020s is not a straight line. It is a winding road of curiosity, patience, mathematics, and engineering. Science rarely announces its practical applications in advance. Kunst did not know he was building the foundation for contactless surgery tools. He just wanted to measure the speed of sound. That is how science works. Curiosity first. Application follows. We take away a lesson about wonder. The world is full of forces and phenomena that operate just outside the reach of our senses. Invisible, silent, powerful. Acoustic levitation is one of the most visible demonstrations of that invisible world. A physical object floating in air, held in place by waves you cannot hear, moved by mathematics you cannot see. It is not a trick. It is not an illusion. It is physics, doing exactly what physics does when you understand it deeply enough, making the impossible look effortless. If you made it to the end of this video, you now know something that most people walking past you on the street do not know. The air around you is not empty. It is full of force, full of potential, full of physics waiting to be harnessed. We would love to know what application of acoustic levitation surprised you the most. Was it the drug research? The biological cell manipulation? The NASA applications? Leave your answer in the comments below. We read every single one, and the conversations that happen down there are genuinely some of the best discussions on the channel. If this is the kind of content that makes you see the world a little differently, we would be incredibly grateful if you hit the subscribe button. Every subscriber helps this channel keep going, keeps these stories being told, and keeps the world of hidden science a little more visible. Until next time, keep asking the questions that sound strange. Those are always the ones worth asking.